afternoon. Thank you very much for the opportunity to present some information about the Catch for Oxyfuel technology and the Catch for Climate project. Okay, presentation should be now visible to everyone. Very brief introduction to myself. I'm a process engineer working with Polysius for roughly 12 years, 13 years now. During the last years, my main focus has been the development of the oxyfuel process, and now accompanying the further commercialization and the prototype installation. And it's a great pleasure for me to show you some general information about the oxyfuel approach and also some insights to the Catch for Climate project. So first of all, Polysius is working on a so-called solutions portfolio covering different approaches of oxyfuel. There are different ideas to realize the oxyfuel process depending on the project case, whether it's a new build kiln line or an existing kiln line, whether there's some switchable plant operation possible, meaning to run the plant with air and with pure oxygen, or directly to build kiln line that is primarily designed for the pure oxyfuel operation. And for revamp solution, there are also concepts to add separate oxyfuel calciners. I won't go in detail regarding those three approaches on the right. However, to show you some context here, what role the oxyfuel technology, and especially the pure oxyfuel technology, plays in the portfolio. And the basic of the oxyfuel process is the idea to deliver a most efficient and sustainable method to capture, to enrich CO2 right in the process. This is, of course, based on the conventional clinkering process you all know very well, so nothing to say about that. But then the next step, the oxyfuel principle in clinker production, which has been discussed for roughly 20 years now, is to substitute the combustion air, the oxidizer in the process, by pure oxygen, and to allow the existing kiln design to run with this pure oxygen. There's usually a notable amount of gas recycle required, because otherwise the gas volume would be much less than in conventional operation due to the missing nitrogen in the air. And this is basically feasible and has been discussed for many plants. There are also already some plants under construction using this approach. It's adapting the well-known principle. However, there are some challenges regarding this recycle stream while allowing the conventional plant design to be operated in oxyfuel mode. It creates some additional effort. For example, the heat to the raw mill needs to be transferred from the raw gas via a gas heat exchanger, which is traditionally not a very favorable approach, because in the future, I will give some details on that, in the oxyfuel future, the false air tightness is becoming much more important than it is today. And based on this nowadays first generation of oxyfuel, Polysius developed a second generation, which incorporates already all developments we see to make this process even more efficient. This relies on a new build preheater and calciner because it's designed to a much lower volume flow, and the basic principle is based on feeding the pure oxygen more or less solely to the firing process. Let's say 15 years ago, people often ruled out that it's possible to run the kiln with pure oxygen. The follow-up slides, I will give you some insights why this is feasible. And we also gain a couple of benefits using this new approach. First of all, some equipment is not longer necessary. The kiln line runs without a large gas recirculation from raw gas to the cooler, so this saves some equipment. There is no tertiary air duct anymore, which also eases up the topic of sealing the kiln system against false air intrusion. And also, what is quite attractive, there is no gas-gas heat exchanger for the raw gas required. As a matter of fact, the pure oxy-fuel, the second generation oxy-fuel, delivers much more cooler vent air with a higher temperature, which is usually way sufficient to link the raw mill to this cooler vent air. Some other modifications are necessary due to the oxy-fuel process itself. For example, the bypass is operated as a closed system without a stack. All the bypass gases are returned to the kiln line, either to the calciner or to the clinker cooler. And the changed atmosphere in the sintering zone also bears the potential to produce even higher clinker quality in the future. Furthermore, there's a strong potential for waste heat recovery due to the elevated cooler vent air temperature, which is in the range around 450 to 500 degrees C. That allows a good temperature level for the waste heat recovery and power generation. Let's have a look a bit more into the details. First, the question, how is it possible to operate the sintering zone with this more or less pure oxygen while maintaining the required process parameters? And the clue in this approach is that due to the low gas volume of the oxygen compared to the nowadays secondary air, all the oxidizer is fed to the kiln, while only roughly 1/3 of the oxidizer is consumed by combustion. So the flame temperature actually is moderated by this very high oxygen excess, and all the oxygen which is not taking part in the combustion still needs to be heated up, like the nitrogen nowadays in the sintering zone. And by this approach, we can maintain the same temperature in the sintering zone like in nowadays conventional clinker kilns. There's some other modifications. Instead of feeding the fuel with air, which is not possible anymore due to the nitrogen content, the fuels are transported with some pressurized CO2-rich flue gas. This is a general requirement in oxy-fuel plants, since air is not a suitable pneumatic transport medium to feed material or fuel to the kiln line anymore. And then due to the high oxygen concentration, the burner design can be a bit more simplistic than nowadays high momentum burners that are designed, for example, to be used with secondary fuels, due to the fact that the high oxygen concentration always allows a good ignition and combustion of the fuel. So by this concept, it's well feasible to run the sintering zone with this very high oxygen concentration And then the next question is what to do with the precalciner. The precalciner, there's a different approach. The precalciner is fed then with a kiln flue gas containing roughly 45 to 55% of oxygen, so still a high oxygen concentration. However, due to the entrained flow reaction, all the combustion heat released from the combustion is directly converted into chemical reaction enthalpy in the temperature range about 900 to 950 degrees C. So despite the high oxygen concentration, it's also then feasible to run the calciner on the used temperature range due to characteristic of the calcination reaction. The higher CO2 partial pressure causes a slightly raised calcination temperature. We expect something around 40 to 50 degrees C. In this case, there's a higher solid gas loading due to this less volume flow. On the other hand, we can apply smaller ductwork for this smaller gas flow, which allows or sustains high fruit numbers, which ensure that the material can be still transported pneumatically in the calciner and the preheater. And the lower gas volume flow also notably shifts the capacity flow rate in the preheater, improving the heat exchange between gas and meal and allowing good heat recuperation in the preheater. In the development phase, this also has been intensively investigated by the Barracuda virtual reactor CFD package, which is capable of simulating entrained flow reactions. There's also the principle to first add some hot meal and after that the fuel into the calciner, because ignition is no longer an issue, but it shall be ensured that there is some hot meal, some calcium carbonate in the gas stream to absorb the heat from the combustion as soon as that takes place. And like some plants already have today, there is the option to do some meal and gas staging, a meal and fuel staging to improve the combustion and maintain a sound temperature profile in the calciner. So these are two major aspects how the kiln line can be operated while feeding the high concentrated oxygen to the clinker cooler. Let's have a look to the Catch for Climate project. As already mentioned, this is built and operated by a joint venture from 4 cement producers, namely Heidelberg Materials, Butzi, which has in Germany the branch Dückerhoff, then Schwenk Cement and Vicar are part of this joint venture, and they're right now building in southern Germany this 450 tons per day pilot cement plant, or let's say pilot clinker kiln. It comes without an own raw meal production due to the fact that it's in the vicinity of an existing facility which can actually supply raw meal, and already a nearly finished installation and of the kiln, and right now cold commissioning is going on, and we expect the hot commissioning end of this year. Let's have a look into the project Catch for Climate. While it's a very small kiln with only 450 tons per day of capacity, it is at least as complex as a large-scale industrial facility. The really new aspect is that the kiln line not any longer is the major part, but it's the new plant consists of 3 major plant sections, namely the CO2 supply, the oxygen supply, which is not that sophisticated here due to the pilot character, but there's a kiln line with an extensive flue gas cleaning, which is necessary to deliver cleaned flue gas to the subsequent CO2 purification. Dirk will give some information on that after my presentation. And that really renders this project with a high degree of complexity. No matter whether it's has a capacity of 450 tons per day or 4,500 tons per day. There's also this newly developed bypass cycle. There's a multi-stage flue gas cleaning, including NOx reduction, including SOx, mercury, etc. And this is in this degree of complexity really something new for the cement industry. Also, that there is a much stricter standard on the flue gas composition after cleaning at the interface to the CO2 purification unit. Unfortunately, I had the time to translate all the description here, but I hope that the symbols in the flow sheet are explanatory itself. If there are any questions afterward, just let me know, then we can explain it a little bit more. While we executing this project, I will highlight some challenges that are evolving in the oxyfuel technology and the application of oxyfuel in the cement industry, which are a bit different from what we know from today's plants. A major part is the gas tightness. Of course, gas tightness is always relevant, and the less forced air intrusion is encounters in a current cement plant, the more efficient the process can run. On the other hand, sealing all the gaps in an existing plant can be quite an effort, which is not always economically viable. However, in the future, the gas tightness is really a key aspect of a well-operating oxyfuel plant. At the end, CO2 purities way above 95% CO2 are required. For final products, even above 99%. And this means that the higher the CO2 concentration already is in the clinker burning flue gas, the more efficient it can be purified. And especially the non-condensables are of particular relevance, mostly oxygen, because the final product often requires very strict limits regarding non-condensables, especially on oxygen. There are oxygen limits as low as 10 ppm in the final product. That also means that small fluctuations in the oxygen concentration in the clinker flue gas are already relevant regarding the CO2 purification efficiency, and that leads to the conclusion that the plant really has to be gas tight, and in a completely different way than it's usually gas tight today. So this led to a lot of considerations regarding the design of the plant, and we had a holistic walkthrough through all the forced air relevant parts in the plant to avoid false air wherever possible. This applies to all sealings, especially the rotary kiln sealing, all flanged sealings. There's a solid design required, also offering sufficient lifetime and good maintainability. For sure, it's important to have the plant tight at the beginning of the operation, but the tightness is necessary to be maintained over a year and then also be maintained over a couple of years from revision to revision. So this is really a new challenge to maintain this high tightness. And this is not only relevant for static sealings, but also for rotary kiln sealings, but also for any material in and outlet and all rotating moving parts, they require special attention, especially the outlets where, for example, kiln dust is leaving the backhouse, where bypass dust is leaving the backhouse. These material outlets also need to be really sealed to avoid any forced air intrusion. This also led to a bunch of internal guidelines regarding flange, ceilings, welds, etc., to ensure that the kiln line is as gas tight as possible, especially the equipment downstream the combustion. False air before the combustion is already a nuisance, but at least oxygen from the false air then can takes part in the combustion and is converted to CO2. But false air downstream the calciner is even more critical because it not just lowers the CO2 purity, but also increases the oxygen concentration. So this is first overview about the Catch for Climate project regarding the kiln line technology. Thank you very much for your attention.
Okay, thank you very much, Josh. Very informative information for the project. Let's go to the next presenter. Could you give us about the oxygen production and related technology? Is the floor is yours.
Yeah, sure. Give me a second to share the screen.
Josh, could you unshare your stop sharing first, Josh? Okay, thank you very much. Dirk, we can see your presentation right now. Could you start, please?
Yeah, okay. Good. Unfortunately, my camera is not working. So
it's okay.
Thanks for having me in this.
We can see your face in the presentation already.
Yeah.
Okay.
That's why I introduced this slide here. I think I got introduced already. I'm the project manager on Linde side for this project here in Mergelstetten, the CI4C project.
Mm-hmm.
And during the presentation, I will touch this project whenever this makes sense. But I will start with a few words about Linde in general, as I'm not sure if you know about this company and what we may have to do with cement and lime companies. And I understood that from these two areas, the audience is mainly. Linde is basically known as a gas company, and this has to do as quite often you see trailers on the road in hospitals, you see barrels with gas. But we also have a strong engineering division in the organization, and the engineering division is in TEPC company, so we have our own technologies. But also can work and have done so with other technologies from any third parties. And our focus is on providing engineering services to the customer, including procurement and construction activity. While gas is focusing on the gas part and providing services around gas. And together, it's a quite unique setup to have here the best of gas supply and engineering. And you may wonder, hey, why he is talking about this, but I think after the presentation, you will get an idea why this can be beneficial for your business as well. Very quick, this is focusing on the EMEA, so the Europe project, but we are not only dealing with cement and lime industry clients from there, also many other big industries. I go quite quick through this to have more time to the question how Linde can support the decarbonization of the cement industry. Joost earlier talked about this part, your plant. Let's assume you're planning to erect a new pure oxy-fuel kiln, which is not our business. So Linde has not to do with this, but you have to think about downstream and upstream things related to these projects then. So at first there comes this oxygen supply in place. We as Linde are a leading company in this business to provide air separation units, ASUs. There are others as well, no doubt, but we have a quite strong position in the market here. And sorry, here we go. And let's focus today a bit on the downstream part, so the CO2 processing part. And as you will see, there is a bit more than just these capture unit. Typically, a CO2 processing unit consists of a preconditioning, compression, purification, drying, and rectification part. For the rectification part, you need a refrigerant unit. This is from time to time a bit different setup as the details here depending on the input from the source, in this case here the kiln, what kind of materials are used there, so what impurities are in, what's the CO2 concentration, the expected one. There can be a fluctuation, but roughly, and also, and this is very much important then for farther downstream, what is the requirement on the output of these CO2 purification unit? What quality is required? What impurities are not, and where to go? But in any case, this liquefaction is necessary as here the CO2 separation takes place. Well, after we have the CO2, the question is what to do with this. And there are several options. And this is also really a thing where you have to think early in the project about, as this is driving the setup of the CPU itself. There's there is on one side, that's in the top right, there's the possibility to have gasified product, gasified CO2. And this goes then into a pipeline and goes somewhere. Different possibilities. A bit similar is the so-called supercritical CO2. In the industry, we can talk about supercritical. In the public, we should avoid this because some people interpret supercritical with very dangerous in regards to health and safety, but it's just a thermodynamic condition of CO2. Has some advantages. And the other thing, you can have liquid product at the end. And with this liquid product, again, different possibilities. Truck transport, rail transport, or by ship. As Linde, we can support in any of these things, not only capturing, also with further downstream handling, and as mentioned earlier, also with the ASU part, with the oxygen supply. We have technologies in place which can guarantee a high purity product at the end with a high capture rate. We are able to deal with low flow volumes and also, and this is quite often discussed, hey, can you modularize your plants? Yes, we can. We can also build large modules. But this all depends really on the location where you are building these plants. So this needs to be discussed quite early in the project. Whether you would have a skid build plant as this one in Mergelstetten. It's a comparable small plant. But we also can build stick build. And the advantage of this technology here, which we are using also in Mergelstetten, is we don't need steam because we don't need these amine. And I think you know that amine capturing is one of the possibilities. We don't have it here, so no steam necessary, and also in regards to handling of any kind of chemicals and dealing with the waste out of it is not an issue. And we have quite some references there. As Jos mentioned earlier, it's not a one-way story alone. It's also that the CPU can provide, so to say, some utilities for the kiln. The process condensate, which we have, we can't avoid this. We can't avoid this, and so we provide this to the kiln as well as the so important inert gases, and these on different pressure levels. Different pressure levels as necessary to operate the kiln. This slide shall just show that we have really different kind of technologies, which is on the lower left-hand side shown. There are some of the possible technologies we have, and on the upper side, left-hand side, there is, so to say, an indication low CO2 concentration to higher CO2 concentration. So technically, we are able not only to provide technologies for an oxy-fuel kiln, also for other applications. This is possible. And then, as I think indicated earlier, question how to conditioning this and how to support the logistic. Then later, there are different things in place where we can support. Yeah. This is just, again, an indication that it can support a customer in the entire chain in regards to CO2. I think I can skip this and bring your focus on this web page, which is mentioned on the bottom. If you like, go there and you get a better idea of what we are able to do, what we can do, and yeah. And as already indicated in the beginning, you need to think a bit. You will have a lot of questions. You will face quite some challenges. Just a couple of them. And earlier in the Mergelstetten project, we also faced some projects. We had a joint tie-in hazard, and we discussed process questions a bit and defined best solution. And we found it. It's not started yet. We are in commissioning phase, as was mentioned earlier, and but I'm pretty sure that this plant will run and prove the technology. Well, all these questions, as I said, with the different technologies we have in place, we can support in answering questions regarding, hey, how to deal with these specific ROGAS conditions and these product specific conditions, as they are really different from location to location. We have a lot of experience in engineering execution, so do we need redundancy concepts? Yes, no. To what extent? This heat integration topic, which is coming more and more an important role. Plot limitations quite often are challenging. We have experience to find solutions. Unfortunately, sometimes involved with additional costs, but at least they work. And as indicated, also the CO2 transport, we have solutions which supports the client. And finance is always a topic, and we have here different business models. I will come to this in a second. And due to the fact that we have the gas organization, which has a lot of experience in regards to operation of a plant, which also we are getting as a feedback from them and putting this into our engineering, then this is an advantage. And in case you will decide, hey, might be better that somebody else is working with this, we have quite some experience with remote operation concepts. So the slide you know from the beginning, and really the combination of these two worlds, engineering and gas, is an advantage for our customers, as we can support from the early beginning and including after startup, after operation, as we have also a service department for our clients. There are different business models available, and with all we have good experiences, build, own, operate, where Linde Gas is owning and operating the gas parts, which has also advantages for the clients which are using either the gas or supplying the gas. There are joint ventures like this project in Frankfurt with Heidelberg, and sale of plants, yeah, of course, also one of the benefits. And not only the CO2 capture as a service, it's also the entire chain up to the storage. We can support you guys if you wish. In case you will contact us, yeah, some information. I think my colleague Van Pong is in the audience. He may help you in regards to one or the other question, and later I can share the slides as well. Some references quickly. With these oxy-fuel technologies, we are familiar since years. We had a CO2 plant together with an ASU plant back in the early 2000s with Vattenfall. It's a coal-fired power plant, and they wanted to decarbonize their plant. So it's, of course, a different technology, but somehow comparable. And the flue gas was then treated and CO2 captured and liquefied at the end. Next step, a little bit higher, is the Mergelstetten project, which is currently running. I think you was mentioned already about the project, about the partners. No need to repeat this. We here in this plant, we are capturing the CO2 then. It is a comparable small plant. It shall demonstrate the process, but on other sites we demonstrated that also with larger capacities we can do so. Here in Mergelstetten we are producing only 24 tons liquid CO2. And the quality of this CO2 shall be food grade, so quite high quality with less impurities, but meanwhile also for sequestration quite high requirements are in place. That's this already mentioned Langford project, this joint venture, also here food grade quality at the end. And a bit different, much larger. It's for Java chemical industry in the Netherlands. 3,000 tons per day liquid CO2, but the quality, even it is not food grade, so to say, but the quality is quite comparable. But this is then for sequestration in the North Sea later on.
I am sorry to disturb you. Be a little bit run
All
out of
fine.
the time. Could you just make a summary in a few minutes, please? Hello. Okay, just make a summary.
Yeah. I think this is here the for you probably the real important thing. The oxy-fuel kiln is so to say the bread and butter business for you guys, and you want to decarbonize this. And from experience, I can say this is really possible, but requires a close, good relationship between all the involved partners. We have discussion about these inert gas very much, quality, pressure, reliability, etc. And you need to be clear on both ends what you require. And I only can highlight this and say, hey, when you start a project, please have this in mind. Don't underestimate here the thing on such a slide. It looks easy and it's feasible, it's doable, absolutely, but requires some meetings to clarify topics. I'd like to say this. And a bit similar with the ASU, as the quality of the oxygen also differs and needs to be clear what is required. This is, what to say, probably the most important thing when you start a project. Talk with us, and don't forget to bring the involved parties together so that everybody can share their concerns, their requirements, etc.
Okay, thank you very much just to share our some information about your technology, both the oxygen and about the on the before and after the clean process. Are there any other questions from the floor? Please raise your hand.
Hello, I have a question. Regarding to your project, Cash for Climate project, how do you produce the oxygen that is close to the plant, or you transport from somewhere else?
It's coming from somewhere else. In this particular case, there is a oxygen storage, and the oxygen comes from air separation unit somewhere else. In this particular case, for the Daegu plant.
Okay, and the second one is, what is the most suitable technology for oxygen generation, particularly on the cement manufacturing process?
ASU, an air separation unit.
Okay.
You need this at the end because you need I think you can confirm this, you need continuously oxygen, and therefore you need an ASU on site.
Yes.
With these vessels, that's good for this demonstration plant, for this particular project here in Mergelstetten. But for a large commercialized driven project, you need an ASU.
Okay.
Okay, thank you very much. A round of applause for the session
Thank you very
number
much.
4.
Thank you for Josh and thank you very much.